it's changing is some polynomial with degree 99, you know, et cetera, et cetera, et cetera, et cetera, right? But exponential functions increase at exponential rate. Yes?
So I have an idea. This might be a bad idea, but if we know that it's the derivative is some constant k times e to the x, can't we just pick a point, just like 2 or something, and then just solve for the tangent line at that point, and then that tells us what k is?
Okay, that's an interesting idea. Let's do it. He says let's solve a simpler problem. Let's take this function, f of x equals e to the x, and let's just try to compute a derivative. Yeah, actually this is a brilliant idea. He says let's try to compute, let's put aside this problem of trying to come up with the derivative in general. Let's just try to come up with the derivative at a single point first and see what happens. Sound good? All right, how about the so-called magic point, so-called by me and no one else? What is the derivative of e to the x at the magic point? In other words, just what is the derivative of e to the x at 0? Just do it by the definition. Yeah. Okay, so we do it. F prime of 0 would be the limit as x goes to 0 of f of x minus f of 0 all over x minus 0. And that turns out to be what? You guys with me? Okay, f of x would be e to the x. What's e to the 0? 1. Anyone know how to do that limit?
It's not the exact same thing as over there.
Yeah, it is. That's what you're supposed to be realizing right now. Yeah, this limit, which is in fact, by the definition of the derivative, the slope of the tangent line to the function at 0, actually is this missing thing. Damn. All right, so now instead of k, I'm going to replace k with, this lesson's going really well. I'm going to replace k with a new understanding, which is that Gehart, the derivative of e to the x is e to the x times some constant, and that constant is whatever the slope of that tangent line is, which I don't know right now, right? So in fact, I've reduced the problem of finding the derivative in general to the problem of just finding the derivative at 0. All right, so look, we have to do this now, okay? And doing this is really hard, all right? So I'm going to give you a proof right now. First of all, does anyone know the answer?
Yeah.
Yes.
Yeah, probably maybe a lot of you know the answer, or 5 or 6 of you. What's the answer?
1.
Okay. Who did?
Wallstein. I remember
Wallstein
this.
taught it. Great.
Oh yeah.
Anyway, what's the answer? This is not. This is. There are no secrets in this custom. What's the answer?
1.
Yeah, this is 1. This is 1.
I was actually thinking, it has.
Yeah, kind of looks like 1, right?
Yeah,
it looks like 1. Yeah, I think it's 1. All right. So I'm going to prove this now, and I'm just going to warn you that you might not like this proof. That's because there's no really good way to do this. So this proof is going to be slightly wishy-washy, but only slightly wishy-washy. So it's more or less going to be okay. But Mateo, we're going to fix it later, in a week or 2. So here comes a slightly wishy-washy proof of this particular limit. All right, let's do it. So I have the limit as h goes to 0 of e to the h minus 1 over h. And, various algebraic suggestions are all going to fall apart. Conjugate, nonsense, it's not going to work, factoring, no. Somehow we need to use properties of E itself.
I suggest this.
So I can think of only one thing to do, but it's so horrifying that I'm very reluctant.
Put the limit in the limit.
We're going to put the limit in the limit.
Oh
I mean, this is pretty much what you were talking about, right?
What?
We need to put the limit in the limit. There's only one thing I know about E, and here it is. And unfortunately, if that's what E is, that's what E is, man, and there's no other thing I know about E. And so, I have a choice of which one of these to put in. Which one seems like a good idea to put in?
The bottom.
The bottom one, yeah, because they're both going to 0 or something, so that seems like that might be a good idea. All right, let's do it. Performing this monstrosity, so this becomes the limit as h goes to 0 of... And advanced use of brackets are now going to be required.
The limit.
Everything's going to be all over h, so can I just put a 1 over h down here?
Yes.
That seems like a good idea. On the outside. And now the top is going to be some stuff to the h minus 1. So now there's something which is going to be raised to the h power minus 1, and that thing, e, is a limit. It is the limit as a goes to 0 plus of 1 plus a to the 1 over a. Good so far?
Yes.
Alright, so just catch up for a second. And now I have to do something with this mess. And there's pretty much just one good thing to do. Yeah, what should we do, Yob?
You can say that A and H are basically the same thing.
Yeah, that's a, you guys buy it?
Yes.
Yeah, Yob, I think they like you better than me. If I had said that, they would have been like, yeah, A and H are basically both going to 0. So this is the slightly wishy-washy stuff, which will say that look, if they're both going to 0, let's just call them all the same variable. All right. So if we're willing to accept that for the moment, then this becomes instead the limit as h goes to 0 of. Now all I'm going to do is replace every a with an h because they're basically the same thing. We sort of agree. Jump. Now we have this huge thing. And then this becomes to the h. And that is 1 plus h. 1 over h.
Now we can kill stuff.
Yeah. Yeah, Kendall goes. Just the entire building just collapses now, right? So I have something to the 1 over h to the h, which is
Just the thing.
something to the 1. So now I have just 1 plus h. You following this? Don't blink,
Yes.
you'll miss it all. Then minus 1.
So it's just H,
So that's h times
Over
1 over h.
which is 1.
There it is. It is pretty fancy. Okay, so I have just done many exciting things, which is I just proved that the slope of the tangent line to the e to the x curve is in fact 1, and also that, and therefore I've solved the limit. So okay, whoa. The derivative, it turns out that the derivative of e to the x is e to the x.
So it doesn't.
What? So this is a function which at every single moment increases at a rate of whatever the value of that function is at that point. If you go to x equals 1, for example, and you ask the e to the x function, what are you about to do next? In other words, how fast are you increasing? The answer is he is increasing at a rate equal to his own value. Pretty exciting. All right, so that's incredible. I had like 4 more things to say. Oh yeah, suppose we try this trick again with 2 to the x. What is the derivative of 2 to the x? Take 45 seconds and go as far as you can until you're stuck.
Yes.
I got that. Is that what you got? Sorry, I'm going really fast. Shivani, cool? Okay, in other words, please interpret. Shivani, what does it all mean?
So it's just gonna
that the derivative of 2 to the x is 2 to the x times a constant.
Times a constant, yeah. So not just e to the x increases exponentially, but in fact any exponential function increases at a rate which is exponential. And one more thing to note, what is this limit?
That's 0.
It can also be interpreted just like before as the slope of the tangent line to the 2 to the x function. Whatever that is. And hint, it's not 1. it turns out to be like around 0.69.
Oh.
And I'm not going to make any further comments about that at this exact moment. But it is not a nice, pretty number. And in fact, the entire reason why we use the e to the x function so often in pre-calculus, I have noticed over the years that when I have taught this to students, there's a certain percentage of the class, like half, is kind of just like, I'm not into this e thing. Why do you keep talking about it a lot? What's up with this whole natural log? I'm going to stick to my log-based terms, thank you very much. And math teachers, there seems to be this gap between math teachers' obsession with e to the x and students' usefulness of this concept. And the answer is that this... What?
You can't like graph.
Yeah, you can't graph things on the ticks. It's all about the ticks. Okay, good. Good. We're having we're really discussing our feelings today. It's great. So, yeah, why are math teachers so obsessed with this function, and why is this function useless? Because this is the real exponential function, and everything else is like a big joke, imposter. This function is so important and beautiful because its derivative is itself. The slope of the tangent line to the curve at the magic point is 1. For every other pathetic exponential function, though it might fit nicely on the ticks, it has a slope at 0 which is ugly. And thus, the derivative of 2 to the x is 2 to the x times some disgusting constant, which is not 1. Follow? Not only that, okay, and now I can finally say the last thing on this subject, which is that our textbook does this totally just disingenuous, just like cheat. That's like they should be embarrassed and disgusted with. That's right, I'm calling you out, Larson.
Oh my God.
They say, yeah, they define e to the x. If any of you guys read chapter 1 closely, which I encourage you to do, or no, maybe it came up in this chapter on derivatives. I can't remember, or on limits, I think. They actually gave a definition of e. Did anyone notice the definition of e that our textbook?
I mean, I've been reading it, so maybe.
Maybe it just came upon it, and then you just blew it off. It defines e to be the limit as x goes to 0 of e to the x minus 1 over x.
What? How do you know?
Yeah, just with a straight face, Larson just says, as we all know from pre-calculus, e is defined to be the limit as x goes to 0 of e to the x minus 1 over x. What? That's not what e is. And thus, our textbook executes this proof by just saying that this is 1. Wait, I think I'm messing this up. Yeah, I'm messing this up. I did this yesterday also. What I meant to say was, e is the number such that this limit is 1. Yeah, that makes more sense. The other thing was wrong. E is the number such that this limit is 1. Okay, now that makes more sense. Sorry. What I said before was stupid. They define e to be the number. They define e to be the number such that this limit is 1. In other words, they execute this proof by saying that this is 1 by the definition of e. But that totally just like obliterates the fact that you have seen e before in pre-calculus, and it was not that, right? E was you found so.
Like a number.
E is a number. Okay, good.
2.7.
All right,
Yeah.
done with this rambling business now. Let's go over homework for the last 15 minutes, and I guess that's all we'll do today. I thought this homework was kind of hard.
Here we go to like.
There's one really hard problem, this double parabola problem.
Wait, which one was that?
And then there were other problems that were also hard.
Actually, that's
Let's do one other problem, and then we'll do the double parabola problem. By the way, this class is starting to get kind of hard. So some of you might need to step it up. That means like coming to math help. I know this week there was a snow day, but Tuesday I expect to see all of you, unless you are 100% perfectly getting every single one of these problems.
So problem 111.
111 and 73. Does that sound good?
Yeah.
Okay. Going kind of fast. Number 111 said, find the tangent lines to the curve y equals x cubed minus 9x through the points 1, negative 9. Okay, we have some function f of x equals x cubed minus 9x. I'd like to know what this function looks like, so I'm going to write it as x squared minus 9, which is really x minus 3x plus 3. Okay, so I'm pretty happy now because I have a pretty much good idea about what this polynomial looks like. So let me just make a sketch of this, because that is what you do in math. You graph everything. This is going to be some kind of an odd function and behavior like this. All right, and let's get some, oh, and then what was the actual, before I graph it, they also said that I'm interested in the tangent lines through the point 1, -9. All right, well, what happens when I actually plug 1 into this function? What do I get? -8. So that's kind of important to know, so I'll do that now. 2, 3, 4, 6, 8. So the function actually goes through the point 8. So the first thing to observe is 1, -9 is definitely not on the function. Like that's key. And since this function is odd, when I plug in 1, I get -8. When I plug in -1, I should get 8. So I'm starting to feel like I have some sense of this thing. It's going to kind of come up, maybe like so, down, maybe like so, and then back up again. Agree? Okay. And then the point 1, -9 is definitely just off the curve, but slightly off. Sorry, 1, -9. All right. Now, haven't done anything yet, just making a picture and being neat and careful. I think this is like slightly wrongish. But I don't know. Okay, next. What am I actually supposed to be doing again? Oh yeah, find the tangent lines to the curve. All right, well let's draw them. There appears to be a tangent line that looks something like that. So I'm not sure how accurate this picture is, but I feel like that's decent enough, right? There's a graph, there's a point, the point's not on the graph, there's some tangent line which goes through that point and through that function. So actually this is very similar to a problem we've done before, right? What should we do? Since we don't have a lot of time.
-9 minus f of x over 1 minus x.
Yeah, but first,
Label the point.
yeah, give the point the name. What would you like to call it?
A.
A, so if that's A, then its y coordinate is a cubed minus 9a. Okay, now that I have given the point the name, I may now discuss what the slope of this line is. And the slope of this line, I can think of it in 2 different ways. One way, it's the derivative at that point, yeah. So let's take the function. Man, it's really great that we have the power rule, so taking the derivative is very easy. It's just 3x squared minus 9. And if that's the derivative function in general, the derivative at a will just be 3a squared minus 9. Follow?
Yes.
Okay, so this is, on the one hand, the slope of this line is just f prime of a, but on the other hand, the slope of this line is
a cubed minus 9a plus 9 over a minus 9.
exactly, can be calculated as the change in y over the change in x, given the 2 points that I know. And if I put those 2 together, I should have an equation in one variable, right? So just quickly doing it, I get 3a squared minus 9 is, like he was just saying, a cubed minus 9a minus -9 over a minus 1. And now I just have gotta just do some algebra, right? So see if I can do it correctly. Or some things cancel. Many.
Like all the unknown things.
What's up? Isn't it just 2a cubed minus 3a squared? Yes. Factor out an a squared. All right. So did a bunch of logic, did a bunch of pictures, did a little bit of calculus, did some algebra, and I get that a is either 0 or 3/2. Okay. What's up?
Has to be 3 halves. Yeah.
Okay, let's check it out. So case A equals 3/2. Well, when A equals 3/2, it looks about right, yeah, doesn't it? Yeah, it looks really good. So I'm feeling pretty happy about that. Let's just double check everything. If A is 3/2, well, actually I don't feel like checking. It just works, right?
Yeah.
Okay, boom. Were you supposed to come up with the equation of the tangent line?
Wait,
I guess you were, right? So the slope would have to be whatever I get when I plug. So what is f prime of 3/2 fractions? 9/4 times 27/4 minus 9? Someone back me up here. 27/4 minus 36/4, so that's -9/4. Oh, that must mean that my picture is so bad. Wait, what?
What?
Yeah, because it intersects
I think your picture-
the,
No, the
intersects
one
the
with the
graph
point
at
pass
like
is
the
the
other
one
side.
that-
too.
that's
What's
the
up?
Your
parallel.
picture is bad.
Is it like really bad?
Like not it's upscale.
It's just off scale. It's just you
But
can't.
how would the slope be negative?
Wait, it might just. Maybe like it's on the other side, like.
Maybe the line is this way.
Like it's on the other side
Wow.
of the slope.
Okay, so that means that's crazy. That means my picture is so bad. Good thing I have calculus. That means that my picture really looks like this.
Wow.
Yeah, but whatever. And what about this a equals 0? Is that nonsense or is that correct?
It's correct.
I think it's correct, right? Because actually, what would the derivative be? The derivative would be, this one's easy, I can do it, -9. So that means that not only is there a green marker, someone, me. That means that there's also a tangent line like through 0 or something. I don't even know how to draw this, but something like that, right? But it's just true. The slope is -9, and in fact, I can double check it really quickly because not only is the derivative -9 here, but also if I do delta y over delta x, I do indeed go down 9/1, right? So in fact, there are two solutions. So your picture can be bad-ish enough for you to get the algebra right. Are we good? I feel like we're good. Okay. Perfect 6 minutes, totally insufficient to do the hardest problem yet so far this semester, in my opinion, the double parabola problem. If you can do this, you're just amazing. It's really hard. Here is the problem. You're given a function, f of x equals x squared, and you're given another function, let's call it g. This is number 73. And this other function is -x squared plus 6x plus 5, minus 5 rather. Okay, and now I need to give you now I need to make a picture of this. And look, man, you need like a very, very large, neat, detailed, high-quality picture of this. And they're starting to treat you like adults a little bit in this book, right? Like no picture provided. Yeah. So you have to put some work in simply to make a picture. I'm going to factor out a negative because that seems like a good thing to do. And upon doing that, I get -x minus 3, x minus, no, that's wrong. -x, what is that, -5 minus 1? Okay, so using my Algebra 1 skills, I have factor g, and now I will prepare to make a very accurate picture of these two parabolas. All right, one of them is our old friend y equals x squared. Boom. Wow. Boom. And the other one is the parabola upside down with a root at 1 and a root at 3, 4, 5, which means the vertex will be at 3. And if I plug 3 back into this function, I get -2 times 2 times a negative. So that's 4, which seems pretty reasonable. So there's a vertex here at 3, 4. All of this is helping me graph the function. And then at -5, it's 0. Okay, so this is my graph, which already took a lot of work. I see that there are these two parabolas and they have this relationship with each other. They do not intersect. If your picture is bad, you're going to just get everything wrong. So, what are we supposed to do? The answer is, we are supposed to find the equations of the tangent lines to both parabolas. In other words, if you imagine this as some kind of rock formation, what we are looking for is a line which is touching both of them. So if you dropped this meter stick in there, are you guys kind of feeling it? There's going to be one here, and then there's going to be the other one that's going to kind of be like, right? You can kind of just like, There are going to be two lines there. I will draw one right now. I'll try to. It's quite hard. It's going to hit one parabola, and then it's going to hit the other, like at a different spot. All of this like logic and thinking and modeling is required to begin the problem. All right, and then there's going to be another line also, but for clarity, I'm not going to draw it because I'm hoping it's just going to fall out from the algebra. All right, who's with me so far? Good. Bell's going to ring in 3 minutes. What do we do now? Emma.
So it's the thing that has the derivative at that, like the 2 points are going to be the ones that have the same derivative on that parabola as that parabola.
Yeah, notice she's using lots of words like that and this and pronouns and demonstrative. That's really annoying. If only we had names for these things. That's why I called this function f and I called this function g. Proceed again with your sentence.
Okay, so it's so you can find the 2 points because it'll be the points that have the same derivative as f of x as g of x as that other point. The derivative of that other point of g of x.
Yeah, she's still using words like that other point. What should we do, Ethan? Label the points. Yes, brilliant idea. Let's label this point. What would you like to call this point?
A and B.
A. And let's call this other point B. Okay, if we do that, I mean, this is all very hard, and I haven't even done anything yet. If I'm going to call the point where the function, the point where the tangent line hits the first parabola, if I call that, hits parabola f, I'll call that A. Thus, its y-coordinate will be a squared, follow?
Yeah.
And the point where the line hits the other parabola, I'll call that point B. And this is negative b squared plus 6b minus 5. All right, now what some of you may have done is just set the derivatives equal to each other and be like, oh, I think I'm done. No, totally wrong, right? There's lots of complexity involved before you understand what it is that you're supposed to do. All right, because it's not that you're not looking for a place where the derivatives are the same. You're looking for a place where the derivative of this function is equal to the derivative of that function at a different point. All right, now is it kind of clear what to do?
Yeah.
What must be true about this line? Its slope can be represented in 3 different ways, right?
Yes.
The slope of this line is f prime of a, it's also g prime of b, it's also change in y over change in x. And that's essentially it, right? So I take my function f, which is x squared, f prime of x is 2x, so f prime of a is 2a. On the other hand, my function g is negative x squared plus 6x minus 5, so its derivative is also easily computable as crap. Negative 2x plus 6. So g prime of b is negative 2b plus 6. And it's also true that the slope can be represented as delta y over delta x. So negative b squared plus 6b, not 65, 6b minus 5 minus a squared. Are you following this? Over b minus a. All right, and so now what you do is you have these 3 expressions, and so I now have like a triple equality. That 2a is negative 2b plus 6 is also that negative b squared plus 6b minus 5 minus a squared over b minus a. And even though this looks like one big equation, you can sort of take them 2 at a time, and so you actually have a system of equations you have to solve it, which is still not that easy, right? There's more work to do. All right, who feels like they kind of got this under control? Okay, can I have this homework? If you didn't finish this, well, whatever. I'll just take this homework. This is all I can do, I guess. Okay, Art, you feeling okay about this? You feel like you have to come to math help every day forever? I do. Math is really hard. All right, Irvin, did you hit stop yet?
Not yet.
That was the end of abbreviated lecture 10. Lecture 11 is starting in 2 minutes with a different bunch of kids.
Wait, serious?